Good morning, everyone. Thank you for joining my thesis presentation. So my topic is synthesis and biophotonic property of conjugated fullerene nanomaterials for biomedical application. And under this topic, I have two chapters to talk about. So the first chapter is going to be nano C60 and C70 and fufutin-based photosensitizer for photodynamic therapy. So first, I'm going to introduce a little bit on the photodynamic therapy in the treatment of multi-antibiotic resistant bacterial infection. And then I'm going to talk about our research based on nano C60 and C70 based photosensitizers. And then I'm going to talk about a fufutin based photosensitizer as a targeting antibacterial inactivator for lethal filter killing of MRSA, which is a methicillin resistant bacteria. And then I'm going to talk about some of our future research work. In chapter 2, I'm going to talk about drug delivery for photosensitizer by nanofilament-based stop polymers. So first, I'm gonna introduce a little bit on the polymeric materials for drug delivery, and then I'm going to talk about our research based on the nanofilament-based isopropyl as known as polynipon starburst polymerase drug carriers. Excuse me. And then I'm going to talk about nano C60 based photosensitizer encapsulated by this type of stuff. And then I'm going to talk about some of our research plans. So in first chapter, so since penicillin was found in 1940, only after 20 years in 1960, people have already found the antibiotic-resistant plasmid. And since that time, the increasing of antibiotic resistance keep rising. And in nowadays, the WHO has already announced the antibiotic-resistant bacteria, as known as superbugs, are one of the greatest threats to human health. So that means antibiotic might not be an ideal drug in killing the bacteria has antibiotic resistant. However, photodynamic therapy might be a good way in killing the antibiotic resistant bacteria. So if we take a quick look at the killing mechanism of antibiotic here, so antibiotic will bind on either of the specific binding sites of the bacteria, then slowly damaging that site, then slowly causing the death of the cell. However, for photodynamic therapy, the photosensitizer can bind on anywhere on the cell or inside the cell, and when you give it a light, the reactive oxygen species that's been generated by the photosensitizer will kill the cell instantly. So in this way, the cell will not have time to generate resistance. So the advantage of photodynamic therapy is since they can bind anywhere of the cell, so there's no definite target is necessary for binding. So that means they have a broad spectrum of action. That means one type of photosensitizer might kill many different type of bacteria rather than one type of antibiotics only specific for one type of bacteria. And also, the whole photodynamic therapy process is not temperature dependent. It can be operated under either high or low temperature. And also the synthesizing or discovering the photosensitizer, the process might be might be less time consumer and the cost might be less. And also they have more further research potentials. All these are the advantage of photodynamic therapy. And in nowadays, there are three major photosensitizers: porphyrins, chlorines, and dyes. So one of the good photosensitizer candidates is fullerene, and it's really good photosensitizer candidates comparing with other type of photosensitizer because the fullerene-based photosensitizer can undergo both type 1 and type 2 photochemistry, possibly type 3 photochemistry. So for type 3 photochemistry, I will talk this a little bit in the later slides. And comparing with other photosensitizers, fullerene is more photostable. They don't degrade much under the light irradiation comparing with tetropyrols or some synthetic dyes. And also they have very flexible quantum yield and absorption range. The absorption range of fullerene-based photosensitizer can be tuned into a designed range. And let's talk about type 1 and type 2 photochemistry quickly here, since filtering-based photosensitizer can undergo both of these types of photochemistry. So for the type 1 photochemistry, so once you give it light on the filtering-based photosensitizer, type 1 involves electron transfer. So filtering-based photosensitizer will transfer the electron to oxygen to generate superoxide radical, and the superoxide radical can be used to generate hydrogen peroxide, and then hydrogen peroxide will transform to hydroxy peroxide radical, I'm sorry, hydroxy radical. And the hydroxy radical is one of the killing agents for kill the bacteria. And for type 2 photochemistry is the energy transfer. So the energy from filtering-based photosensitizer will transfer to the oxygen to generate singlet oxygen, and the singlet oxygen can also be used to kill the bacteria. And based on this system, for the filtering-based photosensitizer, we discovered this type of molecule is a very good electron donor, and when conjugated with filtering, they can be a very good filtering-based photosensitizer. And this molecule is called diphenylamminofluorine, short as DPAF. The reason why we choose this molecule as an electron donor is because it's a fully conjugated system. It can donate electron or energy to filtering very efficiently, and also itself has UV absorption around 400 nanometer, which is already corresponding to the blue light that's being widely used in photodynamic therapy. And also, when conjugated with filtering, donor sp3 acceptor conformation will lead to two-photon absorption property of the system. And also, by simply changing the functional group on these two R sites on the DPAF moiety, then the solubility of the whole molecule will be changed. So for example, if we change two R sites into these two long RQ hydrophobic RQ group, then the whole molecule is going to be hydrophobic. And if we use this cationic amino chain, then the whole molecule is going to be hydrophilic. So the solubility of this type of molecule is very flexible. And based on our previous research, we already discovered that when conjugated with DPAF moiety, just simply changing this ketone group into dicyanoyl group, then the absorption band of the whole system will be shifted to the longer absorption. So if you take a look at the line D, this is the green line here. The major maximal absorption band is around 400 nanometer. So if we change the ketone group in dicyanoyl group, the line C, this brown line, then the major absorption band shifts to 500 nanometer. And another thing we noticed that even with more DPAF moiety attached on the C60 ball, it will not decrease absorption of C60 because normally with more modification on the C60 surface, it will break its conjugated system, and then their absorption will decrease. However, with more DPAF moiety attached on the C60, in our case, they will not decrease the absorption of C60 much. If we're comparing E with either C or D, this blue line with either green line and brown line, you will see the absorption of C60 is not decreasing much. So that means the whole system is still remain full conjugated. And also, we find out that we can attach as as four as 40 we can attach 4 DPAF moiety on the C60 surface. However, for this type of molecule, there's still some improvement can be done. For example, we were thinking to increasing the electron or energy transfer from DPAF to the C60 moiety, and also we are trying to get more intense absorption absorption band around 400 to 600 nanometer. And based on all this previous research, we then later on synthesized this molecule. So it's still a C60 DPAF based molecule with a dicyanyl group, which makes the whole system has absorption range around has maximal absorption range around 500 nanometer, and also we use the cationic amino chain to increase its solubility and also the targeting ability on the bacteria, because we know that cationic charge will help the drug to target the bacteria. And this type of molecule is really a good photosensitizer, and we already proved that in our previous study. Under under different light source, either UVA or white light, they all can kill bacteria very efficiently. And the bacterial type can be MRSA or E. coli. So this two figure is this molecule under UVA light, under white light in killing MRSA, and those two is killing E. coli. And another interesting property we find about this type of molecule is they can even operate without oxygen. However, we do need other ion we do need other ion existence in the solution. So if we take a look at this solid square line, then we will see with the existence of other ion and without oxygen, the killing efficiency of our molecule on MRSA is almost identical as the killing efficiency of this molecule under the normal condition. However, without other ion, this hollow square line shows not much killing efficiency. So that means even though we don't need oxygen, but we do need other ion in order to achieve oxygen independent killing. And all the results are showing similar as oxygen independent killing. So we hypothesize the type 3 mechanism. The type 3 mechanism is without the existence of oxygen. However, if we have other ion there, and once the photosensitizer on its triplet states, then other ion might donate one electron to the photosensitizer, then we generate other radical and the photosensitizer radical. And this other radical can furthermore transfer its electron to water, then the water will be will be transformed to a hydroxy radical. Then the hydroxy radical can be used to kill the bacteria. And in this whole process, we don't need the oxygen. So it's oxygen independent killing mechanism. Comparing with type 1 and type 2, we do need the existence of oxygen, because in real case, sometimes we don't have oxygen is existent in our infection area. And if we can use oxygen independent mechanism, then that means this type of molecule can operate without the existence of oxygen. So based on all this knowledge, we then developed a C70-based DPAF molecule, which should have more efficient electron or energy transfer, and also this will enhance their corresponding absorption range, because C70 itself has absorption range around 500 to 550 already. And also C70 is a stronger electron acceptor comparing with the C60. So the electron and energy transfer should be more efficient comparing with the C60 DPAF molecule. So we developed we synthesized and developed this four type of C70 based photosensitizer. So this is C70 ketone DPAF based photosensitizer, and this is dicyanyl based photosensitizer. And these two has two DPAF attached on the C60 molecule. And all of them has cationic amino charged chain to increase their solubility and the targeting ability for the bacteria. And for their UV absorption spectrum, and you can see the data did corresponding to the C60 DPAF based molecule. If we change ketone to dicyanyl, then the absorption band will shift to longer band. And if we have more moieties, then the absorption intensity will increase. And those four type of photosensitizer might have a better potential in the application of photodynamic therapy. And the second type of molecule is we tried to fuse three mono C60 DPAF moiety together to form a trace type of molecule. And this type of molecule contains 3 C60 and 3 DPAF moiety fused within one molecule. And the synthesis of this molecule is based on this trace DPAF structure. And the interesting thing about this trace DPAF based molecule is they have two stereoisomers. And with the help of Professor Wolf, we find out, and he did the density functional theory functional computation to prove the structure, and this cis-cup C9 form will be the major product of these two isomers. So this is the transform. That means two DPF moiety will facing towards the same direction, and one will facing towards another direction. And this geometry is 3 DPF moiety will facing towards the same direction. And we also find that these two stereoisomers can be simply separated by the TLC plate. So we then purified the stereoisomer to get this cis-cup trace C9 form to synthesize this trace C60 DPAF structure. And this structure should have the conformation of cis-cup form that makes all three C60 balls facing towards the same direction. So the reason we're using the lone hydrophobic RQ group here is because this RQ chain is commercially available, and the synthesis step is much simple and easier comparing with the cationic amino chain, and also itself can be a potential hydrophobic photosensitizer, except that this type of molecule, comparing with the cationic type of molecule, they may have more applications, such as in engineering fields. They have a photoswitchable dielectric amplification property, and with the collaboration of Professor Yu in our civic engineering department, we find out when we coat this molecule on the iron oxide gold-based nanoparticle. So this is iron oxide nanoparticle, and we coat a very thin layer of gold on our iron oxide nanoparticle, and then we coat this molecule outside the gold layer. Because the strong interaction between C60 and gold make all these C60 facing towards the gold. And when you shut the light on this type of system, system, the electron transfer from the DPAF moiety towards the C60 moiety will be enhanced by the plasmonic effect of the gold. So that means intramolecular polarization will be enhanced due to the plasmonic effect of the gold. So all these electrons can be distributed on the C60 surface, and this configuration will lead to dielectric amplification. And as you can see the result here, we shut the light on the system for about 1 hour, and once we turn off the light, then the intramolecular polarization will lead to the dielectric increasement. And we compared the trace-based structure with mono C60 DPAF and also this structure, and we find out the trace C60 DPAF based structure did has highest dielectric amplification. And actually, the mechanism here is very similar towards the type 1 photochemistry, which involves electron transfer. For type 1 photochemistry is still the electron transfer from the electron donor to electron acceptor, then further leads to the generation of superoxide radical. So in our design, the photochemistry is still similar here. So this type of molecule can not only used on the photodynamic therapy, but also other type of application. Also, another type of trace C60DPF based molecule we designed is this type of molecule. So based on trace DPAF C60 molecule, we add 3 more DPAF moiety on the C60 ball. So in this molecule, totally we will have 3 C60 as an electron acceptor and total 6 of DPAF moiety as an electron donor. And this type of molecule, we also evaluate its singlet oxygen and superoxide radical generation by 2 of our probe. And this probe, we synthesize this probe to make them only sensitive to singlet oxygen. And the chemistry is shown here. So the probe itself has very high fluorescence, and once it reacts with singlet oxygen, then they will lose the fluorescence. And as you can see the data here, this type of molecule did show efficient singlet oxygen generation. And for superoxide radical generation, we synthesize and use this type of probe. And this probe is sensitive to superoxide radical. So itself doesn't have any fluorescence. And once you treat it with superoxide radical, then the product will have a very high fluorescence. And on the data, we also can see they have efficient superoxide radical generation. So that means this trace C60DPAF based type of molecule can undergo both type 1 and type 2 photochemistry. So they may be a good photosensitizer candidate. And another interesting type of molecule we developed as a photosensitizer is a 15-based photosensitizer. So 15A is a demetallized chlorophyll A, which can be extracted from the chlorella. And this natural product, we actually get this natural product from chlorella. In our lab, we buy a chlorella, then extract chlorophyll from the chlorella. And also the absorption of this tetrapyral ring is shown here. It covers a very wide absorption range, all the way from 300 to almost 700, and they have 2 major absorption peaks centered at 405 nanometer and C60 nanometer, which are corresponding to the blue light and the red light. And the blue light and the red light are widely used in the photodynamic therapy as a general light source. And also, when you give it a 405 irradiation, this type of molecule will generate a very intense red fluorescence around 670. And this property makes them a promising agent for the imaging. So what we did based on the 15-based structure is we developed these 3 type of structure. So for the first type, we connect 2 PEG chain with 2 cationic charge on the end, and we call this LC37. And for this type of molecule, we connect 2 cationic amino chain to make them have total 10 charges on the whole molecule. So we call it LC38+. And for this structure is based on LC38+. We connect the vancomycin moiety on the other side of the tetrapyral ring to make it has both vancomycin and cationic charge, and we call this molecule as LC40E. The reason why we're using cationic charge is because cationic charge can help the drug to targeting the bacteria, and also for vancomycin. Vancomycin itself is a very good antibiotics for targeting and killing the bacteria. Especially for LC40E, when we have vancomycin as well as a cationic charge existing in one molecule, this molecule should have a very strong bacterial targeting ability and also the killing efficiency. So based on these 3 structures, first we test their singlet oxygen generation because 15-based structure can only undergo type 2 photochemistry, which involves energy transfer to generate a singlet oxygen. And as you can see here, we used a different light source, 400 nanometer UV light and white light, and also 650 nanometer red light as a light source to test their singlet oxygen generation. And you can see here, they all three type of molecule, especially for LC40E, generate a very efficient singlet oxygen. And with this promising data, we then applied the drugs on the MRSA to see their killing efficiency. And as you can see in the MRSA suspension solution, the LC40E showed a very promising killing efficiency under both 660 red light and the 405 blue light irradiation. And also they showed promising killing efficiency on the MRSA biofilm, which the MRSA will be a biofilm form, will be a biofilm form to make them harder to kill. Even like this, they still showed promising killing efficiency. And another interesting thing we observed is we also used the human skin host cell as a comparison to see if they can also kill the human cell. If they can kill the human cell as well as the MRSA cell, that means they do have toxicity to the human host cell. However, we find out that they don't have much killing efficiency, much killing ability on the human host cell. If you take a look at this black line E, they almost remain straight. So that means they only have minimal killing ability on the human cell comparing with a very high killing ability of MRSA. So based on this efficient killing ability, we then tried to figure out their targeting ability on both host cell and the MRSA cell. So first, we used the UV-Vis and fluorescence spectrometer as one of our tools to test their ability on both human host cell and MRSA cell. So for the human host cell in UV-Vis spectrometer, we compare these three drugs, and we see there is no obvious peak can be observed for the human host cell. This may due to very low concentration of our drug or very low instrument sensitivity. But that means it's a good thing. That means at least in that system there is not much of drug existent or attached on the host cell. And for the fluorescence spectrometer, we did observe some small peaks for the LC40E and LC38 on the human host cell. However, those peaks still has very low intensity, because you can see here the noise level are already shown here. That also means there is not much of the drug attached on the human host cell. However, when it comes to the MRSA cell, we noticed that the two major absorption peak corresponding to the titropyral ring is shown here, especially for LC40E and LC48. LC48 plus, we observed a very obvious peak that's corresponding to the drug. So that means at least we have some observable drugs attached on the MRSA cell. And also when it comes to the fluorescence spectrum, and you will see the intensity of LC40E and LC38, even for LC37, they all show very intense fluorescence. So that's so that is corresponding to the UV data. So comparing with these two set of data, we can make sure that our drug did has higher binding ability on the MRSA cell rather than the host cell. And based on all these data points, we also made calculation on the host cell and the MRSA cell. And the conclusion is the ratio between the molecular number of photosensitizer on MRSA and the host cell under 1 micrometer area will have the ratio like this. Especially for LC30E, the the targeting ability on MRSA is almost 680 times higher than it on the host cell. So that means LC30E has much more targeting efficiency on the MRSA comparing with it on the host cell. And also, if we take a look at these three structures again, and we will see because of LC40E contains vancomycin and the cationic charge chain, so it has the highest targeting ability comparing with the LC38 plus. And for LC37, it only has 2 cationic charge chain, so it has a limiting targeting ability. The second thing we did is we tried to use confocal microscope to evaluate their targeting ability, because we know this tetrapyral ring will have very strong fluorescence around 670 as a red emission. So first we compared all these three drugs on the MRSA cell, and we observed that for LC40E, it has the strongest red color comparing with LC38 and LC37. And if you take a look at this column here, it's the blue fluorescence emission that we also using as one of the comparison. Because if we go back to the fluorescence spectrum of this type of molecule, you can see around blue light region, they still have some fluorescence. However, we observed that for bacteria itself, they will also generate blue fluorescence due to their cell wall structure. So this column might not be useful for evaluating their targeting ability by the color intensity. And however, when it comes to the host cell, first we use DAPI to dye the host cell, and all this blue color is coming from the DAPI, and this column is the red emission of our drug, and we almost see nothing. We might have seen some tiny red dots for LC40E and LC38, but if we take a look at the overlay image, we can see all this drug is not on the surface or inside of the human host cell. They more likely being trapped by the tissue of the cell or the extracellular matrix of the cell. And according to these dots, it looks like they more intend to aggregate and being trapped inside this tissue rather than targeting or entering in the host cell. And the confocal microscope give us more evidence to show they do have very high targeting ability on the MRSA cell comparing with the host cell. And the last thing we did is we tried to locate exactly where is our drug. So we used TEM evaluation on the targeting ability of our photosensitizers. So on the TEM image for MRSA cell, you can see they have very smooth surface. There is nothing around the surface of the cell. However, when it comes to our drug, with the existence of our drug, especially for LC38 and LC40E, we did observe our drug attached on the surface of the MRSA cell. For LC38, this bubble-shaped stuff is LC38 that's being attached on the MRSA cell. And for LC40E, you can see there is a membrane-shaped drug attached on the surface of the host cell. And furthermore, we use the microtome ultrathin section to evaluating the position of those drugs. And for LC40E, so if we take a look at the MRSA cell first, you will see they still have very smooth surface. There is nothing around the surface of the MRSA cell. However, with the existence of LC40E, then we will see some very irregular bubble-shaped drug around the cell. And this is an enlarged picture. We'll see many irregular bubble-shaped LC40E around at the cell. We also tried to see if it's possible to see if the drug enters the cell. However, we are unable to make decision to make sure our drug enter the cell. Because if you take a look at the MRSA cell only, they have a very it's a very complicated structure. They have many organs or other bio stuff inside of the cell. So even with our drug entered the cell, without without reference, we don't know. We can't make sure that is our drug. For example, we do see some black shades here, but we can't see this is our drug. This is our drug because there it can be some bio stuff inside of the MRSA cell. But one thing we can make sure is our LC40E did has a very efficient targeting ability, and they target around the cell membrane. So, so based on all this research work has been done, we have our research plans for the future in the future. And so for the C60 based photosensitizer, what we want to do in the future is we want to change this hydrophobic type of trace C60 DPAF molecule into this cationic charged type of trace C60 DPAF molecule, because cationic charge will increase the water solubility, and it will also increase the targeting ability. And also actually we used iodide ion as a counter ion to the cationic charge, and iodide might also provide more efficient electron transfer for type 1 photochemistry. And also the same thing for this 6 DPAF based trace 60 DPAF molecule. What we want to do is we might want to change this inner circle with cationic charged chain first. However, we still want to leave the hydrophobic arcuate chain on the outer circle. So in this way, we will have an amphiphilic structure. So all this inner part will become hydrophilic, and the outer part is become hydrophobic. And this type of molecule might have more interesting property, such as the amphiphilic structure will lead to micelle self-assembling, and also the amphiphilic structure might increase the skin penetration. And for 15 based type of molecule, like I said before, the tetrapyral ring itself will only undergo type 2 chemistry, which involves energy transfer. And our thinking is if we can link C60 together with this tetrapyral ring, then we will have a 15 based C60 based photosensitizer. And this type of molecule will undergo both type 1, type 2, and type 3 photochemistry. This will greatly enhance its bacterial killing efficiency. So in conclusion, in chapter 1, we developed a nano C70 based photosensitizer based on our previous study on the nano C60 based photosensitizer, and we also designed and synthesized the trace C60 DPAF stereoisomers, which may have other wide applications rather than candidate as a photosensitizer, such as photoswitchable dielectric amplification. And last, we designed and synthesized functionalized 15-based photosensitizer as a targeting antibacterial inactivator for the lethal killing of MRSA. So in chapter 2, I'm going to talk about drug delivery of photosensitizer by nanofilament-based starburst polymer. So as we know, the effective photodynamic therapy includes a suitable light source, the stability and the toxicity of the drug, and also it also involves a good delivery system. And in nowadays, there are many type of drug carriers that's being used for the drug delivery. However, for the delivery of the photosensitizer, we think polymeric carrier might be a good candidate because of all these type of reason. So in a word, because it's more precise, more efficient, it's cleaner and cheaper. And for choosing the polymeric material for transdermal, especially for the photosensitizer, which being widely used for the transdermal for the thermal treatment, we have to make sure the type of polymer that is suitable for the transdermal delivery. So if we take a look at the skin structure here, so actually the skin structure is amphiphilic structure. And the pathway for transdermal delivery on the skin structure, they normally involves three major pathways, and the most efficient way is transcellular pathway. That means making the carrier or the drug directly penetrate through all the skin layers without making any detour or without stocking at anywhere. So in order to achieve directly penetrating through, then amphiphilic polymer is going to be a good choice. And actually, it is true that people have been using all different kind of amphiphilic polymer to encapsulating different drugs with different releasing mechanism for transdermal delivery. The releasing mechanism is different and they can be for pH sensitive hydrolysis or passive diffusion. However, if you take a look at all these polymers, the most of them is just the linear polymers. So we think if we can use a more advanced polymer, a star polymer, as a drug carrier, that might enhance the delivery ability. If we say linear polymers is more efficient, more precise, is more stable and safer, then the star polymer will have more compact structure, more dense structure, and more capacity comparing with linear polymer. And also it is true that a more advanced star polymer has been used on some advanced technologies, such as thermoplastic elastomer, some car engine lubricant oils, and photoresistant, and there is some star polymer that's been used for drug delivery. And actually, like I said before, for transdermal delivery, we do need a amphiphilic structure to achieve efficient skin penetration. And one type of polymer we find very interesting is this polyisopropyl acrylamide, short as polynipam. So its HMIS is 0, just same as water. It's completely safe and non-toxic. And if we take a look at the structure here, you can see the amide group is hydrophilic and the backbone, and this isopropyl group is hydrophobic. So the whole structure is amphiphilic. And also this polymer is somewhat responsive, which has lower critical solution temperature. LCST equals to 32 degree. So that means once it's dissolved in the water, when the temperature goes over 32 degree, they will shrink and precipitate from the solution. And once the temperature is lower than 32 degree, then will swallow and they were swollen and remaining soluble in the solution. The mechanism behind this phenomenon is still remain unknown or unclear. However, the most acceptable mechanism is shown here. So what happens is when below the LCST, the amide group will have hydrogen bonding or strong interaction with the water group. So all this water will have interaction with all the amide group, makes all the water surround all the monomers, so makes them water soluble. However, when the LCST go over 32 degree, then the strong interaction between two amide group is stronger comparing with the amide and the water group. All these amide group will facing towards each other to make their hydrophobic group facing out, then repelling water from themselves. So what we observed in the solution is when the temperature is below LCST, then the water molecule is around the polymer chain, and the whole stuff is remaining soluble in the water. And once we heat it up, then they will shrink and precipitate from the solution, and they repel water out. So based on this interesting thermoresponsive property, we then developed a polynipam-based star polymer using fullerene as a core. So what we did is we used fullerene as a core, then directly grow polynipam polymers outside of the core by ATRP, by atom transfer polymerization, to form a star polymer. Then the space between all these arms can be used to load the drug. And also, polynapalm itself has LCST as 22 degree. However, when co-polymerized or block polymerized with other type of polymer, then their LCST can be tuned into different temperature. So for example, if we have a second block of polymer on the first polynapalm block, and this second block polymer is hydrophilic unit such as PEG, polyvinyl alcohol, or PAA, this will increase their LCST. Then the temperature will go higher than 32 degree. And if we have a hydrophobic polymer such as polymethyl alkylate or polybutyl alkylate, then the LCST will decrease to lower temperature, lower than 32 degree. So in this way, we can tune the temperature to our designed temperature, because the temperature in the human body is different. It's not the same anywhere. And the advantage of this type of molecule is star-shaped polymer may improve the drug encapsulation ability, and also amphiphilic property will improve their penetration ability. And also, when using fullerene as the core, we will have a very flexible number of arms. We will have very flexible number of arms because the number of arms on the fullerene surface is designable. And also, the fullerene itself only has about 1 nanometer diameter, comparing with some cross-linked star polymer, which is macromolecular level, which has about micrometer level. So they are smaller, more dense, and may have higher drug loading ability. So based on all this, first we developed several different type of multifunctional fullerene core as an initiator. So this is the first type of initiator we designed, and it has total 10 initiating sites. And as you can see here, the synthesis process is very simple to achieve. And also we used a benzene ring here to increase the rigidity of the whole molecule. So this will make all these initiating sites facing outside of the environment to make them easier to make them easier to react with the polymer monomer. But however, there is some drawbacks of this type of molecule. So first, the number of arms or the number of the monolith group on the fullerene core is very hard to count, because they are all the same. They are all on the fullerene surface. So one monolith on the fullerene surface comparing with 5 monolith on the fullerene surface, there is no obvious difference on the proton NMR. So we cannot make sure exactly how many arms we have on the fullerene surface. We can only by TLC or the color change of the structure to determine approximately how many arms or how many monolith units we have on the fullerene surface. And also, for the whole synthesis process, we have to use pure fullerene to begin with, and we know that fullerene has very low solubility. Even in toluene, the solubility of C60 in toluene is about 1 grams to 700 milliliters of pure toluene. That means we have to use a very dilute solution to begin with, and this will result longer reaction time and lower yield. And the second type of molecule we designed is this type of molecule. It contains total 12 initiating sites and total 6 monolith units on the C60 surface. And what we did is we first synthesized this mono C60 monolith-based structure. So this structure only has 1 monolith or 2 initiating sites attached on the C60. And based on this structure, we then add this azide-based monolith on the surface of C60. Then we will then by comparing the proton NMR, then we know exactly how many arms we have on the C60 surface. So for example, the proton next to the azide group is shown here, and the proton of this methyl group is shown here. So by simply comparing the integration ratio between these two peaks, then we know exactly how many arms we have on the C60 surface. And also the next step is also simple. We click the same initiating structure on the other group, then we will have a homogeneous C60 based initiator with 12 initiating site. Also by checking the disappearance of the other group, because other group will become this 5-member ring. By taking a look at the disappearance of the other group, we can make sure all the initiating site that's been clicked on the structure. And also we know that the maximum amount of monolith can be attached on the C60 is 6. So that means when we have Hexakis C60 based structure, then the C60 ball itself will become TH symmetry. So all these different carbons on the C60 ball will only become several peaks shown here. Then they become TH symmetry. So both with hydrogen, with proton NMR and C13 NMR, then we can characterize the structure. And also, the advantage of this type of molecule is we use the C60 monolith, a mono-monolith based structure to begin with. They have very good solubility in the solvent, so we can do a very concentrated reaction. This will reduce the reaction time and also increase the yield. And also another advantage of this type of molecule is it's very easy to change the initiator anytime. So this time we clicked this initiator on the other group. We can also click other type of initiator on the other group to make them has more ability to do other type of polymerization. So so as an example, the third structure we designed is this structure. It's pretty similar as the second structure, still starting from this this molecule, and on the other group we clicked this initiator, which has 2 initiating sites to begin with, onto the other group. Then total we are going to have 22 initiating sites, comparing with the second structure, which only has 12 initiating sites. So that also proves that it's very flexible to click different type of initiator on that. And also, the fourth structure we developed is this type of structure. And this type of structure, what we did is we actually cut down the number of initiating sites into half. So we cut this arm. We changed this arm into a terbutyl ester group. And in this molecule, totally we only have 6 initiating sites. The reason why we do this is because the terbutyl group is very easier to be changed into other type of functional group only by the transesterification or transamidation. So for example, we can change here into other type of initiator that's been that is suitable for ring opening polymerization, or we can change it into other type of initiator that's been suitable for cationic or anionic polymerization. So that means the whole initiator will have 2 types of initiating site on that. Then the polymerization might be done by different methods in situ. So that means we can do both atom transfer polymerization together with cationic or ionic or ring opening polymerization in situ at the same time. So this type of molecule is even more flexible. So based on these 4 different initiator we developed, so first we try to use our first structure to prove that the polymerization of polynipam by ATRP is controllable and living. So first we use the nipam monomer to grow the first block of polynipam group outside based on our multifunctional filtering core, and then we continuing grow this terbutyl acrylate monomer as a second block. So we proved that the polymerization is living and controllable by using our multifunctional filtering core. And the second pathway we did is we tried to use this structure with 12 initiating sites. So first, still the same. We use ATRP to grow the first poly-nippon group. However, for the second block, we changed the bromide group into the azide group, and then we click the second block directly on the first block. So we synthesize the second block first to make sure they have homogeneous chain lengths. And then we just directly click the second block on the first block. Thus, we will have this type of molecule containing both poly-nippon block and polyterbutyl acrylate block. And comparing two methods, this method has much better advantage rather than the first method, because by graph onto methods, we will have more homogeneous polymer, so we will have low PDI, and also because we're using this chain to start to begin with, then we will have more homogeneous chain lengths, and also the reaction time is much less than the first reaction, because click chemistry is very efficient. The reaction time of this reaction only takes about 3 to 5 hours. However, for this reaction, it will take about 8 hours to overnight, and also we have to use a little bit higher temperature. So what we did next is we used this star-shaped poly-nippon polymer to do more modification. So first, what we did is we just simply hydrolyzed this terbutyl group into the carboxylic acid group, and we find out this type of star polymer will have both pH sensitivity and the thermal responsive ability. So that means under different pH value, their LCST is different, because the interaction of the carboxylic acid with different environment under different pH value will result in different solubility. And also, we find out with the chain length about 150 of Nippon group to 25 of carboxylic acid group, then the LCST at pH 7 can be controlled around 35 and 37 degree, which is corresponding to the human body temperature. Even with two variable factors, this type of molecule may still have some potential applications in some specific area of the human body, such as female womb, because in female womb they have different temperature and a different pH value. So this type of molecule still has potential as a drug carrier. And the second thing we did is we tried to changing this terbutyl group into our cationic amino charged chain, and we find out that under the ratio between Nippon group 150 units and the cationic chain group about 20 units, we will have LCST tuned to about 37 degree. And actually, this structure is more pH independent. So we can say under different pH value, they all remain the similar. LCST, because the cationic charged chain is more pH inert compared with the carboxylic acid chain. And there are other reasons why we want to use our cationic amino charged chain, because first, the cationic amino charged chain is water soluble. This can be used as a hydrophilic second block to tune its LCST to higher temperature. And also, the cationic charge can be used to targeting the bacteria, and also it will enhance the protein binding. For the protein binding, it might have potentials in the application of biosensor, or in the application of biosensing or other type of protein involved sensing chemistry. And also, this type of molecule is not pH dependent. That means under different pH value, we only have one variables to control, that is LCST. So we can easily control its temperature to make sure the delivery is more controllable. And also due to the charge-charge interaction between this cationic charge and the cationic charge in our drug, then the loading ability of our photosensitizer might be higher by using this type of molecule. So next, what we did is we tried to test its loading ability. So we use this type of molecule as a drug carrier, and we use this prototype C60DPAF cationic charged molecule as a prototype drug. So we try to load this structure inside our stock carriers. And by simply taking the UV vis absorption of the drug, then we will know the loading ability, the loading ability of our star. So what we did is first we mix them two together, then take a UV vis, then we will see the absorption of our drug is shown here, both orange line and the black line. So for the black lines, we used the linear shaped polynippon and the cationic charge polymer as a comparison. So we used this linear chain as a comparison, so shown as a black line, and the orange line is our star. And once we load the drug, then we take out the carrier, and the remaining, the free drug remaining that's been remained in the solution, we take the remaining solution again, and their UV vis absorption is shown here. And as you can see here, the free drug concentration is very low after being loaded by our star. And for the linear polymer, after being loaded by the linear polymer, the drug concentration decreased, but not as much as the star. And also, I took some pictures here to show that the loading efficiency can be visualized by just taking a look at the color of the drug. So our drug has a brown color shown here, and this is the linear polynippon cationic charged chain. And you can see before loading they are brown, and after loading they grab the drug and precipitate out, then stick on the side of the bottom stick on the side of the bottle, and you still see the remaining free solution is still brown. However, when it goes to our star, once they grab the drug, then precipitate out from the solution, you will see the remaining solution become much more clear or colorless. So that means the loading ability is higher than the linear shaped polymer just by visualize it. And we also did the calculation based on those data points, and we find out that for our star polymer, it has about 86% loading efficiency, comparing with the linear polymer, which only has about 30% loading efficiency. And comparing these two, the star polymer will have almost 3 times higher loading efficiency than the linear efficiency. And for the application of this type of system, I think what might happen when it comes to the real case is before the treatment, the infection area of our human body will have higher temperature, higher than 37 degree. And once we treat them, when we treat the infection area with our system, then they will aggregate and localized on the infection area to cure the infection area. And once the infection area has been cured, then the healthy tissue or the healthy body will have the temperature at 37 degree. That means higher temperature will drop below their LCST. Then the whole system will become soluble and will become and will solubilize in the biosystem and can be digested away by our body. So based on all this structure, the system might have one drawback, that is if we take a look at the mechanism here, so once we hit the polymer, so all the polymer will shrink or the collapse, then hold the drug inside themselves. However, in some case, if we want to release the drug outside of this carrier, that might be harder to achieve. So what in our future research, what we might do is we are going to add a linker like this blue color, very short linker, or a trigger between the linear arm and the multifunctional core, and this linker will be reactive oxygen species sensitive linkers, since we are loading photosensitizer, and photosensitizer will generate reactive oxygen species. So it's going to be reactive oxygen species sensitive linker. And all this linker has been proved to be reactive oxygen sensitive, such as supercarrier radical hydrogen peroxide or singlet oxygen. So for example, if we use this structure as a linker, then once we treat it with singlet oxygen, then it will break from here. So if this side connects with our C60 and this side is our polymer, and once this double bond breaks, then the polymer chain will be released from the multifunctional core, and in this case our drug will also not be held inside of this space. So we might design we might design and synthesize this structure in the future to make them have more drug releasing efficiency, and also we will do some biomedium test based on all this type of system. So in conclusion, in chapter 2, we design and synthesize different type of fullerene or multifunctional core as an initiator for star polymer synthesis. And also we design and synthesize the nanofullerene based polynippon star polymer as a potential photosensitizer drug carrier. And also we did a short test on the drug encapsulation ability by our fullerene based star polymer with one of our prototype drug. So in overall, in chapter 1, I talked about the design and the synthesis of nano C60 and C70 and P15 based photosensitizer. And then I talked about killing and targeting of MRSA by P15 based photosensitizer. That is our future research plans. In chapter 2, I talked about nano C60 based multifunctional core as an initiator that can be used for different type of polymerization. And also I talked about fullerene star polynippon as a photosensitizer carrier. And then I talked about the fullerene-based photosensitizer drug encapsulation by C60-based star polynippon carrier. And also I talked a little bit about our research plans in the future. So at last, I want to thank my advisor, Professor Chen. He really gave me a lot of help during my study. And I also want to thank my committee member, Professor Chris, Professor Wolf, and Professor Cho. They also gave me significant amounts of help and suggestion during my study. And also, I want to thank our collaborator, Professor Dai and Dr. Dai and Dr. Liu in Mass General Hospital, and also Professor Yu in Civic Engineering Department. Also, I want to thank our previous postdoc, Dr. Wang, the whole chemistry department, and my family in supporting me during my study. Thank you very much.